Assalamualaikum and hello everyone. My name is Rahman Izal bin Ahmad and my matrix number is CE250103, and today I'll be explaining question 1 A and B. So we move on to question 1 first. Evaluate the following double integral, which is double integral over region R 2xy squared minus 4x cubed dA, where R in bracket xy 1 less than x and less than 2, then -1, less than y, and less than 1. Next, we move on to the manual calculation. So, the first step is we spread the term using subtraction rule, where we get 2xy squared dy minus 4x cubed dy. Then, we integrate it and we get the answer, which is 2 over 3x, 2 over 3xy squared minus 4x cubed y. Then after that, we substitute with the upper limit and lower limit, where you can see it became minus here. So the upper limit, we put it in the first subtraction, then the lower limit in the right side of the subtraction. Then from there, we get the answer 4 over 3x minus 8x cubed. Then we integrate outer the outer part, where we use the same step as the first one. We split it uh, using the upper limit and lower limit, where the first upper limit goes into the left side of the subtraction and the lower limit to the right side of the subtraction, and we calculate it using calculator. We get the answer equals to -28. Here is the software solution that I'm using the MATLAB platform to prove the manual calculation was correct. I type out the script and it gave out the answer, which is -28, and it is the same as manual calculation, and it also gave us the 3D graph of the supposedly the 3D shape. And in this slide, I will explain in detail on the script for the calculation that I'm using in MATLAB. So for the script, the green text is just to point out what I'm doing, and the gray text is the actual coding. First, the clear and CLC. It clears all variable from memory and wipes the command window to prevent calculation error. And since xy initialize x and y as symbolic variable. So the important part is the F1 and the calculation. For the F1, it stores the mathematical integral in variable F1 using explicit programming. So after that, we not need to type out the calculation again. We just need to type out F1. So ans underscore 1a and initial execute nested double integral and from inside and out. The inner int integrate with respect to y from -1 to 1, and the outer int integrate the result with respect to x from 1 to 2. And after that, we run the program, and the script output is -28, which is perfectly verifying our manual calculation, and it also shows us the 3D surface plot generated via mesh grid and surf that I typed in the coding to visually map the function behavior directly over the rectangular region R. Next, we move on to question 1b, which is double integral over region R x plus y dA, where R is the region bounded by y equals to 0, y equal to x squared, and x equal to 1 over 3. Next, for the manual calculation, we did it the same as question 1a, but this time it's simpler. So first, we integrate with respect to y, and after we get the integration, we substitute the upper limit and lower limit into the equation, where we get the answer, which is equal to x over 3 plus x to the power of 4 over 2. Then for the outer integration, which is with the respect to the x, we did the same as the first one. We integrate it and we substitute the upper limit and lower limit. Then we subtract and we get the answer equal to 17 over 4860. Next, for the software solution, uh, I'll explain it in detail in next slide. But here you can see the script that I typed out, and after we run the simulation, we get the graph and the same answer as the manual calculation, which proves that our script is right. You get to see the answer, which is 17 over 4860. Next, I'll be explaining the script for software solution in MATLAB and the graph. So as usual, we define the integrand function first, which is f2 equal to x plus y. So we doesn't lose our function. And next, the most important part is the evaluation of the double integral with variable limits. We put in the nth underscore 1b equals to int in bracket int in bracket f2 y 0 x to the power of 2 of bracket x 0 1 over 3 and of bracket. So the integration order matters a lot here because the inner boundaries depend on x. So we must integrate with respect to y first, so the variable resolve properly into a final constant. And the rest of the script is just for displaying the answer and for plotting the 2D bounded region R in xy plane. As you can see, we display and print and print. So for the 2D graph, I found some example that I can use, and I changed the value that match to the question, which is 0, 1 over 3 and 200 for x code and y curve equal to x codes and power of 2. So this is the script that we use for plotting the graph, and after that we run the MATLAB equation with MATLAB script and we get the answer that prove our manual calculation.
Assalamualaikum. My name is Amirul Shakir bin Kamaluddin. So my message number is DE240127. So I will explain about question 2, which the question is by changing to polar coordinate, evaluate double integral x square y dA where r is the upper half of the analysis bounded in between x square plus y square equal to 1 and x square plus y square equal to 4. So for the question 2, the question asks to evaluate double integral x square y dA, where r is the upper half of the analysis between the circles, which is x square plus y square equal to 1 and x square plus y square equal to 4. So for the step 1, we need to convert to polar coordinates. As we know, s equal to r cos theta, y equal to I sin theta, and dA equal to r dr d theta. Therefore, x square y equal to r cos theta square times r sin theta equal to r power of 3 cos square theta sin theta. So for step 2, we need to determine the limits, which is the region is the upper half of the analysis, which are inner radius equal to 1 and outer radius equal to 2. For next step, step 3, we need to separate the integrals into radial integral, which is the answer is 31 over 5. And for the angular integral, it is 2 over 3. So for the step 4, we multiply the result, which is the final answer is 62 over 15. For the software solution, I use MATLAB to verify the analytical result. The integral was defined in polar coordinates, and MATLAB's integral2 function was used to perform the numerical double integration over the same limits, where r range from 1 to 2 and theta range from 0 to pi. The MATLAB result was 4.1 4.1333, which is equal to 62 over 15, which match the manual calculation exactly. This confirms that the solution obtained using polar coordinate is correct. In addition, a 3D surface plot of fxy equal to x power of 2y was generated to visualize the function over the upper half annulus region. The plot shows that the function remains positive throughout the region and reach larger values near the outer boundary, which contribute to the final value of the integral.
Assalamualaikum. My name is Muhammad Hakim bin Shabuddin and my metric number is DE240147. So today I will present you about my question is question 3. So the question is, by using double integral, find the surface area of the portion. The parabola z is equal to x square plus y square and the below plane z is equals to 1. So this is for manual calculation. So the given question is z is equal to x square plus y square. So the given z is equals to 1. So first step we must use the surface area formula. So x equal to the double integrate square root 1 plus differentiate z over x square plus z over y square differentiation square times with the dA. So since z is equal to x square plus y square, we must differentiate it first, x square and y square. So differentiate x square we get 2x, then differentiate y square is we get 2y. Then we substitute it back to the formula. Then step 2, we must determine the region the parabola is cut by the plane z is equal to 1. Since z is equals to the x square plus y square, we substitute the z equals to 1 from the given question. So this is a circle of radius 1. So because the region is circular, it's easier to use a polar coordinate. So let x square plus y square is equals to r square and dA is equals to r dr d theta. So the surface area will become the s square s equals to the 0 to 2 pi and 0 to 1. So square root 1 plus 4r square r dr theta. So as you know, 1 plus 4 r square is from there. We convert it to the polar form, polar coordinates. So we evaluate the integral. So let u is equal to 1 plus 4 r square. Then du is equals to 8r dr. This is we differentiate it and we get a r dr over r dr equals to du over 8. Then we substitute it back to the r square root 1 plus 4 r square dr of equals to the 1 over 8 to integrate 1 over 5 1 to 5 u 1 over 2 du. Then we integrating 1 over 8 times with the 2 over 3 u power 3 over 2 is equal to 1 over 12 u 3 over 2. Then we applying the limits 1 over 2 times with the 5 power 3 over 2 minus 1. Since 5 power 3 over 2 is equal to 5 square root over 5. We get a 1 over 12 times with the 5 square root over 5 minus 1. So then we integrate with respect to theta. So the s is equal to 1 over 12 times with the 5 square root 5 minus 1. Uh, we we integrate with 0 over 2 pi d theta. Since integrate 0 to 2 pi, d theta is equal to 2 pi. So the final answer will be x is equal to pi over 6 times with a 5 square root of 5 minus 1. So that is the answer for the manual calculation. This is software solution that I using MATLAB. So let me teach you how to use a MATLAB and write the coding in here. So first step, in line 1 and 2, first I use a clear to remove all existing variables from MATLAB memory. Then I use CLC to clear the common window so the outputs appears clean. In the line 5, then since command create a symbolic variable, we use symbolic variable because MATLAB needs them to perform the differentiation and integration analytically instead of numerical calculation. So the variables are x and y for Cartesian coordinate, r and theta for the polar coordinates. So in line 8, this line defines the surface equation. The parabola is represented by z is equal to x squared plus y squared. This equation will later be used to find surface area. In line 11 to 12, the differentiate function calculates derivatives for differentiate z x. Let differentiate the function with respect to s. As the result, differentiate z over s is equal to 2s. For differentiate z y, is we get 2y. This different this differentiate are required in the surface area formula. So in the line 15, this line creates the surface area integrand. So the formula is square root 1 plus differentiate z over x square plus differentiate z over y square. So the MATLAB substitute the derivatives automatically. So the expression becomes 1 plus 4x square plus 4y square. In the line 19, the subs function means substitute. Since we want to integrate over a circle, polynomials are easier. So we replace x squared plus y squared is equals to the r squared. So it will be square root 1 plus 4x squared plus 4y squared become 1 plus 4r squared. So the multiplication by r comes to the from the Jacobian when converted from the Cartesian coordinates to the polar coordinates. So therefore, dA is equals to the r dr d theta. This is why r is added to the n. So in line 23, this line perform the double integration. The inner integral in3 integrates with respect to the r from 0 to 1. The outer integral integrates with respect to theta from 0 to 2 pi. So this calculate the total surface area over the circle region. In line 27 to 29, this command display the answer. Display prints a little chart, convert to the symbolic answer into text format, double convert the symbolic answer into a decimal number. F prints the result neatly on the screen. So in the line 33, the mesh grid function creates many points. So these points are used to generate the 3D space plot. The radius range from 0 to 1 and the angle range from 0 to 2 pi. For the line 34 to 36, this line convert polar coordinates into Cartesian coordinates. So x equal to r cos theta, y equal to the r sin theta. Then MATLAB will calculate z is equal to x square plus y square for every point on the grid. So in the line 38, the surf command generates the 3D surface. It draw the parabola using all calculated points. In line 39 and 42, this command label the axis and add a little to make the graph easier to understand. For the line 43, this command sets MATLAB to the default 3D viewing angle so the parabolic can be seen clearly. So this is answer for our MATLAB coding. The answer is 5 times root of 5 times 5 power 1 over 2 minus 1 over 6. So basically, we get a same answer with the manual calculation, and the numerical value is 5.3304. So this, as you can see in the graph, we get as for parabola. For my question is z is equal to x square plus y square.
Hi, my name is Muhammad Fahmi bin Muhammad Mansur. My matrix number is CE250099, and I was responsible for answering the question 4. The question is, by using triple integrals, find the volume of the solid G bounded by planes y plus z equal to 1, y equal to x square, and and z equal to 0. This is the manual calculation for question 4. First, we need to set up the volume as a triple integral, which is v equal to triple integral bounded z dv, and we need to establish our limits of integration by looking at our bounds. Z varies from the bottom plane z equal to 0 up to the slanted plane, which we rewrite as z equal to 1 minus y. Next, for the y limits, uh, we look at the intersection, setting z equal to 0 in our plane. Equation give us y equal to 1. Since our other boundary is the parabola y equal to x square, y integrates from x square up to 1. Finally, to find where the parabola intersects y equal to 1, we set x square equal to 1, which give us our outer x limits from -1 to 1. And then we can set up our equation, which is v equal to our first integral limits is -1 to 1, and our second integral is x square to 1, and our last integral is 0 to 1 minus y, and dz dy dx. And then we can proceed to our first integrate, which is 0 until 1 minus y dz, and the result for the integration is 1 minus y, and we proceed to our second integrate, which is v equal to x square to 1 minus y dy. The result for our integration will get 1 over 2 minus x square plus x power of 4 over 2. If And then we can proceed to our the last integrate, which is v equal to -1 to 1 over 2 minus x square plus x power of 4 over 2 dx. The result for after of this integration, we will get 8 over 15 unit. That is our g, which is 8 over 15 unit. This is the software solution for question 4. On the left side, as you can see the coding that we use to get our solution. The software that we use to get this is MATLAB software. And on the right side, you can see that the result of the coding, which is consists of the G bounded value and the 3D graph. You can see that the value that the coding get is 0.5333, or the exact amount is 8 over 15. And on the bottom side, you can see a 3D graph. The blue surface represents the top slanted plane y plus z equal to 1. The flat gray base is the z equal to 0 plane, and the red curved wall represents the parabolic cylinder y equal to x square. The visual model confirms that our integration limits correctly capture the exact shape and the volume of solid G.